Welcome everyone to our video on enthalpy. In this video, we are going to define both internal energy and enthalpy. We'll talk about energy and how it's transferred in chemical reactions between the system and the surroundings. And then we'll look at different ways we communicate changes in enthalpy. Recall that the total energy contained within a chemical system, its kinetic energy, energy due to motion, and its potential energy, energy due to forces of attraction, is referred to as the internal energy or the thermal energy of a chemical system. Now, internal energy cannot be measured directly by just measuring a system or some chemicals just sitting there at rest. The only time we can get a measurement is when there's an energy, or in our case, heat, transfer between the system and the surroundings. So when do we get this type of transfer? Well, that's during a chemical reaction. So we cannot measure internal energy as is, but we can measure changes in internal energy. Mathematically, we see this change written as delta U, that is the change in internal energy, is equal to the heat that's transferred plus any work that's done by the system on the surroundings. Now, work in this case is referring to pressure volume changes. Good example would just be thinking about a balloon that is on the top of a test tube that's producing some gas, and the gas expands the balloon. So there's work done increasing the volume of the balloon. What we want to do for our purposes is to simplify this equation and get rid of one of these terms. And the term we want to get rid of is the work term. Now, this is a fairly easy thing to do because in most chemical reactions that we will be studying, there is no meaningful pressure volume work. Hence, the W value is equal to 0. In this case, the change in internal energy is approximated by the heat transfer. The reason why this simplification is important is because measuring a heat transfer is a fairly simple thing to do in many chemical reactions. We talked about it already when we discussed calorimetry. We can measure a heat transfer by knowing the mass of the substance, its specific heat capacity, and measuring a temperature change. So those are all things that are, in the grand scheme of things, fairly easy to do. And if we can measure the heat transfer and there's no work done, that heat transfer gives us an approximation of the internal energy change that's happening during a chemical reaction. In this special case, where we can approximate the internal energy by Q, we refer to the thermal energy in this specific situation as the enthalpy. And when we talk about a chemical change that involves a heat transfer, the change in enthalpy is given by the symbol delta H. This is an energy term, so the SI units for enthalpy are joules. However, you'll see that in most situations, we will be using kilojoules because that is the magnitude at which most chemical reactions that we will be studying occur. So delta H is an approximation of the change in internal energy. Specifically, it's talking about a change within the system. So right now, when we're talking about the enthalpy change, it is talking about the perspective within the chemical system. Delta is a difference, and it's the difference between the products and reactants. So specifically, it's the enthalpy of the products subtract the reactants. If the products have a lower internal energy than the reactants, then that delta H value is going to be less than 0. This means that the system has lost some of its internal energy. If the products have more internal energy than the reactants, then the delta H value is going to be positive, in which case that tells us that the system has gained some internal energy as it's undergone a chemical change. Let's contrast what we just saw on the previous slide with our heat value, Q. So recall from calorimetry that Q is measured in the surroundings. If delta H is less than 0, that means the products have less energy than the reactants. So the system has lost some internal energy. Well, where does that internal energy go? Well, it goes to heat transfer to the surroundings. So the surroundings have gained energy. Q is going to be greater than 0. This would be an exothermic change. If delta H is greater than 0, that means the products have more internal energy than the reactants. Well, where did they get that internal energy? Well, it came from the surroundings. That means that the Q value would be less than 0 because the surroundings has lost energy and the system has gained energy. That's an endothermic change. Let's recap what we've just talked about, but let's start from the surroundings perspective, because this is how we are going to experience chemical reactions. Let's imagine a situation where we carry out a chemical reaction and we measure the temperature change in the surroundings. Specifically, let's think of a situation where the temperature has increased through the process of this chemical reaction. If the temperature has increased, that means the final temperature is greater than the initial temperature. And that signals that there has been an increase in kinetic energy. An increase in kinetic energy just means the molecules in the surroundings are moving faster. Well, energy cannot be created or destroyed. It comes from somewhere. In this case, that energy came from a heat transfer from the system to the surroundings. Remember that heat is just thermal energy in motion, moving from one place to another, in this case, moving from the system to the surroundings. This means that the system has lost energy. In a chemical change, reactants were converted to products. And if through this change there's been a loss in energy, that must mean that the products, the end state of this reaction, have less energy, specifically potential energy, than the reactants. So going backwards now, a chemical change occurred in which the products have less potential energy than reactants. That means the system has lost energy. This energy gets released as heat, or thermal energy, and that gets transferred to the surroundings. The surroundings takes up this heat, increases in kinetic energy, in which we measure as a temperature change. If we measure a temperature change increasing, that of course is going to be a Q value in which is greater than 0. By definition, if the system has lost internal energy, that means that the enthalpy, or the internal energy, is going to be less than 0. A common way to represent enthalpy changes is with potential energy graphs, where the vertical axis is potential energy increasing, and the horizontal axis is just looking at the progress of the reaction, where the reactants are always written on the left, and then the products are written on the right. In the left example here, we have condensation, where a system has lost energy. Water vapor is converted to liquid water. Just like in a chemical reaction, we have an arrow that's pointing in the direction of the change from the gas state to the liquid state. And then beside the arrow, we have a delta H value, which tells us how much energy is lost or gained. In this case, the system has lost energy. If we look at the reverse reaction, where liquid water is vaporized to produce water vapor, we have an endothermic reaction. So we see that liquid water is lower in potential energy. 44 kilojoules is put into the system, and our final products are higher in internal energy. Now, we're going to see an important concept here, which is going to come up many times in our course, is the idea that if we have a reversible reaction, like a state change here, the delta H value is the same, it only switches signs. Exothermic reaction, negative 44 kilojoules, is if we reverse the reaction, endothermic, positive 44 kilojoules. So the same magnitude of energy is just switching directions. The most common way that we are going to communicate enthalpy changes is writing them with chemical reactions. There are two ways to do this. One way is using the delta H notation, where beside the chemical reaction, we write the delta H value. So in this case, the combustion of methane releases 802 kilojoules of energy. Delta H equals negative 802 kilojoules. We can also write this as the heat term being part of the chemical equation. In an exothermic reaction, heat is produced. So we are going to write the heat term on the product side. So these two notations indicate the same thing. Delta H being less than 0 indicates an exothermic reaction. An energy term written on the product side of a chemical equation also indicates an exothermic reaction. And we use a similar notation for endothermic reactions. We can use the delta H notation, in which case the delta H value is going to be greater than 0 as it's an endothermic change. Or we can write the heat term as part of the equation. And in this case, because in an endothermic reaction, energy is being put into the system, we write the energy term as one of the reactants. Let's finish up by mentioning a few general notes that we're going to see in action when we start solving problems, but just good to mention right now so we can keep them in mind moving forward. The first and most useful is that enthalpy changes are stoichiometric. For example, if 1 mole of a substance reacting produces 20 kilojoules of energy, then 2 moles is going to produce 40 kilojoules. And then always remembering what different terms are referencing. When we calculate Q through calorimetry, it is referencing a measurement in the surroundings. When we use the delta H is an approximation of internal energy, so it's referencing the system.